Hear me now still? I actually had the mute on, but if it was still playing in the background, that's very interesting. Or was that I hear you reply back? Hey everyone. We'll be starting in about 3 minutes here. Um, that's funny because someone put "I hear you" in text, and then in I thought you could hear me because I was muted. You should be hearing me shortly. Um, so there's a test mark, and I'll look to see when that test mark comes through. Ah, Julian, you can hear me? All right, there should be sound. I have noticed on YouTube that some videos. Eggs? Is that the egg I drew? Start muted. Eggs. I hope the sound isn't going weird. Now I'm going to double check the sound. Ah, okay. Okay. All right. And all right, so what we're going to do is we're going to look at the rest of chapter 4 here. Well, before we jump into everything, so I guess I'll do the horrible thing I don't like, which is actually put my face up. Sorry about this. I do not like this at all. Oh, my microphone's in the video now. Wasn't before. So where we're at, technically, we don't start school until next week. But and I was going to record video lectures, but I figure that having the ability to ask questions while I'm recording these will be good interaction for everyone. So all our due dates and everything are going to be based off of starting next week. I'm posting the changed material and reorganizing Pearson as we go, but I'm continuing the lecture content here so that it's recorded. And these will stay up on YouTube, so you can go back to them, fast forward through them and whatnot. I will work on maybe finding ways of editing them or breaking them into chunks. The nature of the live stream right now, I don't have full capability to do that. Well, I probably have the full capability. I just haven't done it yet, so I'm not going to promise something I haven't done yet. But this will give us a way to interact with the material and move about. Yeah, camera's weird. I look there, camera's there, stuff I'm writing is here. So, yeah, that's why I don't like the camera thing. But just talking and having a slide up can be odd. So I guess this is an attempt to have some visual clue for what's going on. Oh, not that type of visual clue. The modified due dates and everything, I'm starting to put up, and I'm starting to get out. I was not a big Blackboard fan. I'm diving into it a lot more, and doing a lot of work in the evening, and I'm rearranging some things on Pearson. Our goal was to have finished Chapter 4 this week and an exam next week. So next week, all the homeworks and the in-class assignments that are now on Pearson will be due for Chapter 4, and the exam will be the following week. Yeah. Hi. So these videos are meant to be watched along with the course material and the sections. Therefore, I have found in the 4 classes I've done now that the questions in chat do help. So I'm going to keep opening them up as live streams and going through. But don't feel you're required to be in the live stream. I know everyone's schedules are all over the place. I mean, I've got 4 teenage boys sitting quietly in a room, fearing of making a noise between 1:45 and 3:05. Very fearful me. And I know everyone has different things to deal with. So please, I don't want you to feel that you're required to be here for these lectures, but I am going to put them online for the lecture content. It does help me to have your questions. I need me to speak up a bit? All right. How's this? Is this getting a little more volume coming through? I'm going to jack the mic gain up a bit there, and try to position this a little bit better to where this is, and I think part of this is when I look over here, I'm throwing my voice that way, but the microphone's this way, and back of my head isn't as good. So I just want you to be aware of that. Don't try to go out of your way to be here for the lecture time. And we'll work on this. So this is a work in progress. All education is a work in progress. I always say it's a dialogue. It's a form of communication. So when things don't work, send me emails, ask me questions, and we'll adapt. And sometimes I might say, well, let me just finish this thing here, and we'll leave that up, and then we'll work on it. One of the things I found is questions from homework right now. If people send me the Pearson link, I'm going to be recording videos that kind of use the tablet and the screen thing I have here. So, the video will look like this, with me going, hey, do something with the material, work out the problem, do it in steps, coming across. So that will probably be how office hours go. If you need to kind of show me where you're getting stuck on something, we'll work on ways of doing that via Zoom, Skype, whatever format that we can work out. One of the other things I've noticed is getting pictures from cameras of people's papers. I'd say about 6 students, 7 students in general, have been doing that consistently over the last year, and this semester about 4. So it was like 2 last semester. And I do like pictures with cameras, but I'm getting like I've had one person where their photos come out as just lines, and another where I can see the work but it's not legible. I always look at the picture back in your software before sending it, and if possible, get the number of the problem, which is in the upper right hand corner of Pearson. It's usually like 3.2.25 or 3.4.18, where the 3 is the chapter number, the next number is the section number, and then the last number is the problem number. So that's administrative stuff. Anything administratively, email me questions coming across. What I'm going to do is I'm going to talk about the last 2 sections, or the last section, the last 2 probability distributions we're going to look at before we wrap up chapter 4. So this won't be a horribly long lecture comparatively. Where things would have been planning out, where things were planning out, we would have been doing an in-class activity, and having that in-class activity will probably do through a variety of little Pearson things to get the points back in. Also, Gradebook and Pearson is horribly not accepting the exam scores. I'm transferring all of that over to Blackboard. I have Blackboard is my thing. I've been working on it all spring break, and I was trying to use Pearson for the Gradebook, but I'm going to have to put it all on Blackboard. I've got my 092 class up on Blackboard now. I need to get this class and my 162 up, so I am working on that. So I saw Jay asked about group FaceTime. I'm a Pixel user, so I'm not sure I have access to FaceTime, though Zoom is capable of that. I think you can get Zoom from the school, but if we need a group setting, I will find something to do a group setting that we all can access. If we can't do it group, we can do it individual to individual. We'll make it work somehow. That said, I'm going to get started with this on here, and Google Hangouts is possible. So I tend to go towards the Google applications like YouTube for this instead of proprietary things. I'm a Linux user, so I tend to sometimes have some software compatibility issues with things that are written for Mac or Windows. Though, like I said, I used to work for IBM, so I actually get through a lot of those. But I don't like taking the time to fight through them. And since most Google things run through a web browser, I also find students can use those without much headache. So I tend to go towards the Google applications as a way of doing things. But we'll research some things, and we'll play with them as the week goes on. I think Google Hangouts will probably be the first thing I try, and we'll see how that goes. I will be posting a detail of my office hours on the updated syllabi, which I pretty much have the schedule down for those. All right, so again, administrative questions, throw out at me. I'll look at ways of that we can communicate en masse and individually, and we'll get there. So we're looking at the last section in Chapter 4, and it calls itself Other Probability Distributions. So we'll look at what we have here, and they really actually discuss two other probability distributions. So what I want to do is just drop back a second, because we're going to have three probability, well, when we're all said and done, we're going to have four probability distributions we're going to use. We're going to have three discrete and one continuous. And you know, the splitting hairs. I don't like saying untrue things, but the Chapter 5, where we do the normal distribution and we learn its cousin, the student's t-distribution, I think of them as the same thing, but in general they are considered two separate things. So all right, maybe we're going to have three discrete distributions and two continuous, but once you learn Chapter 5, the student's distribution isn't too bad. So the binomial experiment and the binomial distribution, which was the first one we looked at, it is an experiment that you repeat for a set amount of time, or trials, countable trials. You can only have two outcomes for the experiment. It's either going to succeed or it's going to fail. And whatever your probability of success, it's always the same. The example we used in class was the rotator cuff surgery. It had a 90% success rate, and we said surgeon's going to perform three of these. They're always going to have a 90% success rate, and then we could say, well, what's the probability of, which is your variable x? What's the probability of 0 of those surgeries being successful? What is the probability of 1 being successful? What is the probability of 2? was a probability of 3. And we get the probability of exactly those amounts coming out. Now, if we wanted to figure out like groupings of those, we'd use our probability rules. So if I wanted to know, what's the probability of 2 or less, I would add the probability of 0, the probability of 1, and the probability of 2. And so binomial is a very used discrete distribution. This idea of a success or failure and a countable number of experiments is actually fairly common. The geometric and Poisson distribution, which we're going to look at here, if I can do it without my software moving slides about. There we go. The geometric and the Poisson distribution have different parameters than the binomial distribution. And so in your notes, you kind of want to look at when you use the binomial distribution, when you would use the geometric, and when you would use the Poisson distribution. And so if you can kind of have an idea of when you go to these certain things, we'll let the calculators take care of the formula that we have and the equation sheets that you have for them. And so the geometric distribution is a discrete probability, so the things are countable. Okay, and the conditions we have, I hope you can see the pointer there. The conditions that we have is you repeat the trial until a success occurs. So notice you keep going until the success. It's different from the binomial. The binomial, you did 5 trials, you did 20 trials, right? And you always did 20, and you counted the total number of successes. In a geometric, you go until you succeed. Once you succeed, you stop. And each trial is independent of each other, so the probability of success is going to be the same. And so your random variable is the number of the trial where the first success occurs. And so we can then try to find when the first success will happen with a geometric distribution. So what I'm going to do here is I'm going to put a geometric problem up, and we're going to look at how it works. Now notice the equation here is the probability for the first success is the probability of success times the probability of failure to the power of whatever your success variable is minus 1. And what's really happening, and let me pull this over here. Over here, sorry, as I scroll through here. And so what we're looking at is our Poisson distribution, or I'm sorry, our geometric distribution is the probability of success times the probability of failure to the x minus 1 power. And what's happening is, if you notice, these powers are counting how many things you have, right? There's the hidden one in here. We have p to the first power. And so p, lowercase p, is the chance of success. And lowercase q is the chance of failure. And so this actually ends up being very similar to the binomial distribution. Binomial distribution counted all the successes. So p had x up here. And then it counted all the failures, which was everything else left in the number of trials. But here, we're going until we get the first success. So we're going to have one success and one success only. That's why it's to the first power. And then in the failures is everything up until that success. So for example, let me look at the example here. So I'll say this is the example number 1 in the book for geometric distribution. And so I'll put it out here. A study found smartphones failure rate of 43%. Grabbing 4 phones randomly. What is the probability of the 4th phone failing? So how we can see this is a geometric probability distribution is here. We're actually looking for the 4th thing to be the problem. And I guess if we look at the wording on this, it's what is the probability of the 4th phone being the first to fail? So I'll say first to fail, right? Get my English properly there. Remember, I'm the math guy, not the English guy. So this happens a lot in statistics. This is not my chance of failure in my probability distribution. I want to find the thing that fails. So I have a 43% chance of finding the thing that fails. Right? Failure is something we can test for. So using this equation up here, I'm going to change my color slightly here, or dramatically. So my first success, which is the failure of the first phone, is p equals 0.43. The chance of not having a success, well, it's 1 minus 0.43, which is equal to 0.57. So the probability I want to find is what are the odds that the 4th phone is the first one to fail. So now what I'm doing is I'm taking these variables here and I'm plugging them up into here. So I have 0.43 to the first power because I'm only having one success. I'm stopping as soon as the condition I'm testing for is true. And then in 0.57 to the x minus 1. So my x is 4, so that's going to be to the 3rd power. And my calculator comes along and tells me that 0.43 times 0.57 to the 3rd power gives me 0.079632. And what I'm going to do is I'm going to turn this to a percentage. So 1, 2, and so there. So I'll keep these 2 decimal places. So it's 7.96% chance that the 4th phone will fail. And so that's not where the geometric distribution comes through itself. I'm going to switch back to the slide here for a second, but some people will confuse these with a binomial distribution because of the similarity in how the variables are treated here. But remember, our binomial distribution had that NCR part in it, the number of trials choose X, right? And NCX, right? We had a combinatorics going on. This first time, there's always going to be one, always going to be one. So that NCR is always 1, so it doesn't hang out in the front there. but they have a kind of a similar concept going through. You're counting the failures and you're counting the successes, but we stop at the first success. So this power of success is always 1. Coming across. All right. And so that is our geometric distribution. And here's the book's wording on this. And the book's answer, which is printed much, much, much better in the textbook than it is in the slide. I am working on that. That's a Linux to Microsoft thing that I'll fix here, which is why I did it out on the blackboard here. But the thing I want to note is this part here. For the TI-84 Plus, underneath the distribution button, where we found the binomial, we can find the geometric. So I'm going to try to see if I can get my camera to actually show this half decently. I know I had a lighting issue with it. 2 seconds here. I'm going to turn off the light so that the glare might not be as much as it was the other day. And let's see if this will treat me well. So, pulling this over here, and I'm looking down at my TI. I can usually get this camera to adjust, but for some reason I'm still not getting a good focus on it. Alright, well, I think it's trying to adapt too much. For the people with the TI-84s, you have your second key here, and then you have your distribution key here. So if you go to second and distribution, the screen shows a list. And there. And I know they're not in really, really clear, but if you can get to that with the second and distribution, you will scroll down, and there's our binomial PDF, Poisson PDF, which we'll talk about shortly. And then in letter F is the geometric distribution. So you hit enter on it, and then it asks you actually for the p-value. So you put in 0.43, the x value, which we wanted the 4th one, and then we just paste those in, and it prints it out just like the book is showing you. And you hit enter, and you get the same number I calculated. All right, let me go back here. And so that, I know that's a bit blurry, and I do apologize for it, but at least gives you a concept of where things are. And I will work on getting the camera clear so I can record videos on the TI-30s, which I left all my TI-30s in the office. I'm hoping that I think one of my sons has one of my other ones, so I'll try to pull those out, and I will record videos on all the distributions in Chapter 4 on how to use them on the calculator, both the TI-30 and the TI-84s. Again, Google has some good ones also, but notice here in the TI-84 Plus it says geometric PDF, and then it says parentheses 0.43 comma 4. When you actually enter it, it'll ask for the p-value and the x value, and then you hit paste, and it does it like this. The older TI-84s, you'll choose it, and then you have to put in the 0.43 comma 4. All right. And the dog is giving her water, if you hear that in the background. All right, so I want to now look at the Poisson distribution. And the Poisson distributions is a really useful distribution. This actually will lead us to other distributions. It looks at the number of trials or a given interval. And this happens a lot experimentally. And so it's a discrete probability distribution. So again, discrete means there are countable things. And the conditions it follows are that you want to count how many times an event occurs in a given time, or a given area, or a given space, or some set of region that is coming through. And the probability of the event is the same no matter what. The probability is always going to be the same. And if I look at that interval, it's not going to affect any other interval. So different ways and different things that use probability. The example the book's going to use is they look at an intersection, and over a month, so that's your interval, over a month, the number of accidents or the probability of accidents in that intersection, there will be 3 countable accidents within the intersection. It's something that was measured. It was experimentally measured. You counted how many accidents happened on a given calendar month, and you average the results, or you put the results together and you find 3. And so if you want to figure out if one month is greater or less than that given count, your Poisson distribution does it. It is ugly. It is ugly mathematically. It has a very odd formulae, but it looks like this. And so the probability in x, right? So where x is the occurrence in that interval, is the average value that you're using to the power of x. And then in E, which is a special key on the calculator. And again, I'm going to switch over to the calculators here. On all the TIs, it's in the same place except the TI-89s. The TI-89s never put it in a slightly different area. But I will go back here. All right, so over here you have an LOG key and an LN key. And this is for the log base 10 and the natural log. Now above in blue is e to the x, and so you would have to hit second and the ln key to get that. Oops. And that's where you get the e variable. On the TI-30s, it's in a similar place. It's by the left of the numbers and up a bit, and it is still a second key, second, to get the e to the power of. And e is a number that came from banking. It's approximately 2.71818. It's not a repeating. It's like pi. It has no decimal, no given set of decimals. And we tend to think of it as Euler's number. He was the one that kind of clarified it. It's actually probably one of the most useful mathematical constants. But so this distribution uses this constant in it. And notice we also have a factorial down below here, factorial. So we have this two special really keys going on. One of the things that comes out of this, and the book talks about this in problems, but it doesn't do it in the content material. Not me, this. Sorry, peekaboo. All right, so I'm going to come here. So we'll write our Poisson distribution here. I'll change my colors for Poisson. I'm going to go Happy Halloween orange. So P, the probability of a given number of occurrences in the interval is the average to the occurrence times e to the negative of the average all over the occurrence factorial. All right, so that's what we're looking at. So the problem I'm going to look at in the book, and then I'm going to come back here for let's see here. sorry, I'm having a slight slide difficulty here, but I think I'm better now. All right, and of course the slides didn't show. That would explain half the difficulty. There we go. All right, and that's showing in my stream. That's showing. Yeah, so you're seeing the mouse move. And okay, good. That showed back up. Gotta love technology. All right, so we have the mean number of accidents per month at an intersection is 3. What would be the probability that 4 accidents would happen in a month? So I'm going to come back here, and we're going to put this into our probability distribution. So what we want to say is the average number in a month at that intersection is 3. And we want to know what will be the probability of having 4 in a month. Now, one of the things that we can do with this is, because these can go on infinitely. I can go, what would be the probability if there's 100? What would be a probability if there's 1,000? So the distribution doesn't stop, but the probability gets lower and lower and lower and lower as you get further and further away from the mean. And that means that it has a spread. And the standard deviation for a Poisson distribution is the square root of whatever that mean is. So the mean that you're given will tell you what the standard deviation on these distributions are. So we can look at this specifically. We'll say, hey, I'm going to find the probability of 4 accidents. So I'm going to take 3 to the 4th power times e to the negative 3rd over 4 factorial. And I fight that all the way on my calculator, and I get 0.168 or 16.8%, a 16.8% chance. And the standard deviation for a probability distribution that has an average of 3 is equal to slightly bad typing there for a second. There we go. 1.732. Should know this. I just did some square root of 3 things the other day. And so it has a spread of about 1.732. And we'll remember, within a standard distribution, 68% of the stuff is within 1.72 on either side. So if I were looking at my yes, Jay, I'll show how to input the Poisson distribution in a second. I'll look at its spread, and then I'll show the input. So if I have my mean value at 3, then at 4.7 and 1.3, I have a 68% chance of being in there. Now, because they're countable things, the decimals don't matter, but the standard deviation spread comes into play. Now, Jay just asked to show me how to enter that in onto the TI-84. Again, I will, once I get the camera focusing in better, I'll make some clearer videos of these particular components. So let me move this here. And come over. All right, so there's this. So again, this is in the distributions. Yeah, I'm going to find a way to focus this. I'm pretty sure my software can. This is a software control, not a manual control. Keep going crooked here. So there's the distribution, which is the blue key over vars. So I want to go to the second, and distributions. And then I get my listed distributions. That almost focuses. It's almost like it's focusing on a dirt speck on the screen or something. And so you get that out of focus. And if I come down, the Poisson PDF is D. I'll hit enter on that. And it'll ask me for the lambda value. Well, the lambda is the average. So I'll put in 3. And then the x value, in this case, was 4. And then I'll choose paste, and it puts it all together like the book is showing it. Poisson PDF 3, 4. And I hit enter, and I get the 1.6803, and so on that I got before. And that matches what's over here. And thank you for the question, Jay, and also Aisha. I am working on getting a camera that will actually show what is on the screen of the calculators, and I will put videos on. That is my goal. I played with that over the last night, yesterday and last night, because I had another class yesterday and one other one this morning. I will look at a way of getting those recorded clearly. I will say, I'm not the only one that does stuff like this, so Google those up. Google those up. No, Google for other videos that might show that, but I will try to add them there. And so that's where the Poisson distribution works through. And the Poisson is a fairly good distribution. That comes up a lot, because this idea of how often something happens in a given period of time is a very statistical question. One other thing I want to show, because I do ask about spreads a lot, is the geometric distribution has a unique way of looking at its average value and its standard deviation, because you're going until you have a success. And the book again does not do this as in the material. It actually does it as a question. So in section 4.3, question 29 and 30 ask about the standard deviation and the average of a geometric distribution, and they give you the equations there, but they didn't give it to you in the chapter. So just show you what the average is for a geometric distribution, and what the average is for, or what the standard deviation is for. So mean and standard deviation for geometric. The mean is equal to 1 divided by the probability of success, or you can, on your calculator, you have the x to the -1 key. So if you put in the probability of success and hit the x to the -1 key, it does the same thing as this. And so your average on when you first win something is the odds of that happen, dividing into 1. And the standard deviation is the square root of your chance of failure over your chance of success squared. And for your Poisson distribution, well, your mean is given to you in the statement of the problem, and your standard deviation is the square root of the mean. Right? And your calculators and everything are going to call that lambda in Poisson distribution. I don't know. Poisson like lambdas a lot, I guess. All right, that's everything in chapter 4. And the key in these discrete distributions is focusing on the criteria you need for each one. So when we create probability distributions, we take the probability, all the outcomes divided by the chance of one particular event, and that creates the frequency of that, and we can build a frequency table for it. But then when we look at these very particular types, the binomial, the geometric, and the Poisson, we have to look at the criteria for what experiments cause those. And so the experiments we want to look at are going to be, I should say the experiment criteria. Let me scroll, I will scroll. For a binomial, a set number of trials, you can either succeed or fail. Nothing changes the probability of success. It's always the same on each trial. And the variable we're counting is how many successes we have. And we use this notation for them. The number of trials is n, the probability of success is p, probability of failure is 1 minus p, and the successes we count. And we always can count at 0. Right? You can have no success, and you count up to your number of trials. And the equation that we use for that, if it shows up nicely on here, was this. It's that n choose the number of successes, the probability to the power of success, probability of success, I'm sorry, to the power of how many successes you have, your probability of failure to the power of how many failures you have. So notice how these are counting. This counts the number of successes, this counts the number of failures. And this tells you how many combinations you can have of those. And so what makes the geometric really, really odd, because this is the binomial, if we come down and look at the geometric, if we come down and look at the geometric, as I clicked on it and it doesn't show, there we go. This is the same equation. It's missing the NCX part because there's only one. And when you have n choose 1 of something, there's only one combination that comes out of it. So the n choose 1 of 1 is always 1. So we don't write that. And it's still counting the number of successes. This is p to the first, and this is counting the number of failures, q to how many failures there are. So we could say the geometric is a special case of the binomial. And so when we have a geometric, we have a trial, and we're going to keep repeating it until we get a success. And what we end up counting is how long it takes us to get that first success. And then Poisson's distribution is a countable number of things in a given space, or a given amount of time, or some given interval. And that interval will always be the same, and each interval is separate from the other interval coming across. All right, so that's chapter 4. I will be getting all of the quizzes, which would have been the in-class work. Now, I had given you what would have been the in-class work for chapter 3 on a handout. I was going to go over that along with the chapter 4 stuff. What I'm going to do here is I'm going to get an answer key out to the people that need it, and I'm going to try to post a copy of it on Pearson so that people who weren't in class can have a copy, or I'll scan in a PDF. I think my scanner is working of it. So there are going to be 2 in-class things that are the first assignments for next week. They'll be listed as quizzes on Pearson. I have physically handed you the chapter 3 version of that. I'm going to replicate that on Pearson. And I guess since we don't want to just look at a probability distribution, I will replicate that on Pearson for chapter 3. And then I will do the same thing for chapter 4. And they will appear as quizzes on Pearson. so that we get the in-class points for them. And then I'll set the exam with the due date for not this coming week, but the following week. Sorry, I have to look at the calendar. I think it's the end of the first full week of April, right? Because April has a partial week coming up. All right, that's all I have on Chapter 4. If you have any particular problems from the homework should be up until the end of Chapter 4. I'll make sure it is, and I'll arrange all those. But remember, our due dates all start as if classes started this coming week. Yeah, I know, scary faces. But I personally would prefer to leave it like this while I talked. But without having a visual clue sometimes, and the fact that I do pause when I speak, that might be more helpful. I do not like that. I'll go there. So remember, we technically do not have class this week. I am technically recording lectures for you guys to review, where we run over things in the class. But because your questions here have brought some things that I need to do, and the questions are helpful, I will continue to make my recording of lectures as if it's a class. But I can't require you to be here because I know everyone's schedule is up in the air. And so I'll keep doing it in this format. We're really, quote-unquote, starting all the new deadlines and everything next week. All right, if you have any questions, type them into chat. I'm going to stay up here. I'm going to give it about 2 minutes. If you're done, you can log out, and then we'll go from there. As soon as I end this will save online. Usually takes about 2-3 minutes, and then you can access it as a stored video. Have a wonderful day. Be well, be safe, and I'll talk to you soon.